Okay, today we have our second talk of our series of internal seminars. And next week, we will not have a seminar because, as you may know, we already are overloaded with many talks next week. So we will make a small stop next week, and then we will continue with our series of exciting seminars for February 11. No, Anna, can you hear me?
Sí, sí. Can you hear me?
Yes, yes. Okay, we will make a small break at half of your talk, 10 minutes break.
Okay.
It's a coffee break. Everybody can take a coffee, ask questions, make comments, as we did last time. So
yes, I missed
you are free to ask questions and comment, please, in this small 10 minutes break. And of course, you can ask questions during the talk also. Okay, I don't know, Kazushi, if you want to.
Okay. Well, today's speaker is Anna Ferré Mateu, but she's a postdoc on La Caixa, a junior leader fellowship. And today she's telling us about small galaxies. I think some of you have seen an interview on our paper. I think some of the talk on this interview series. And okay, please go ahead. After the introduction, I think we have a small stop for the question.
Oh, yeah, I was going to ask when do you want me to decide when to stop and have a break, or?
Yeah, I think some introduction after the introduction would be a good place to have a break.
Oh,
well, whenever you think it's appropriate, yeah. If you forget, we will remind you.
Okay, let's start and let's just play it by ear. I didn't know about the break, so anyway. Okay, I hope you can see this. Do you see my screen?
Yes.
Vale. So I'm going to start presenting. Vale. Okay. So, well, it may be good that we are going to have a break at some point because this is a road trip. So we're going to be taking several stops. So maybe we can decide which one do we take for a little bit longer. But I'm going to be talking about this realm of compact elliptical galaxies, early type galaxies, through the different mass range. Why we want to do this? Well, so I'm going to be showing this kind of plot for basically all the talk. This is the well-known scaling relation that it's the stellar mass and the size of the galaxies. And for many years, in the realm of early type galaxies, what we know is that at the massive N, we have elliptical galaxies that they follow this scaling relation very tightly, in the sense that more massive galaxies are always larger. And then it goes down towards the realm of dwarf ellipticals and dwarf spheroidals. And then we have the globular clusters that are there. That's a different story. So actually, there are three characteristic mass scales that kind of define, according to the properties of these galaxies, where they are going to be in this plot. And this kind of summarizes this. This is a very nice cartoon from Capillari that shows that you can move from the dwarf irregulars to spirals, ellipticals, just by following these lines. And if you do that, basically, this is a very basic cartoon that shows you that, the other way around, that you can move above this zigzag line, this red line, by, let's say, intrinsic processes, like you grow the galaxy via gas accretion or mergers or so, but there's no external processes in the sense of, for example, galaxy stripping. You need galaxy stripping in order to be able to cross this border. Why do you want to cross this border? You might be asking, because clearly there's nothing here. Well, that was for a long time how it was, but around the last decade, more or less, this part has been populated by all these types of compact galaxies, that they go from the massive N, the compact massive galaxies, down to compact ellipticals, and to the lowest masses, ultra compact dwarfs. So what we're going to be doing today is basically taking this road trip because we want to answer the question whether these galaxies, these compact galaxies, follow a different formation path than what is expected for this more extended branch. And in fact, if we usually follow, if that would be a very crude like scaling relation of what you would expect them to follow from the massive N, what if instead of following this black line, they follow this blue one instead, because they follow the one for compact ellipticals. We also want to see if there's the same way that there was this characteristic mass scale that changes the properties on the extended branch. We want to see if we find any characteristic mass scales that also changes the properties for these compact galaxies. And one of the reasons why we want to understand better all these new type of galaxies is because for a long time they were kind of ignored when making the census, the baryonic census in the universe. But we've been finding them by hundreds, so clearly we need to account for them, and maybe they could help. Maybe they could help alleviate the problem, for example, of the missing satellites. So just before we start talking about each one of these, I just wanted to show or explain very quickly how we think, or what is the most accepted scenario on how to form the massive elliptical galaxies, right? The normal ones, the extended. So it follows a two-phase formation scenario, and this is a cartoon. This is not a simulation, so just be mindful. It's just to exemplify these different parts. So very early on, we have a first phase that it's a dissipative phase, where it happens that up to redshift 2, these massive galaxies that we call a red nugget forms. Is something very compact and very massive already by redshift 2. After this stage, the second phase starts, and it's an accretion phase, where basically this galaxy is going to start growing in size by accreting satellites on the outskirts. So it's going to start accumulating these stars in the outskirts, getting bigger, bigger, until the type of elliptical galaxy that we see nowadays. So I can hear someone. So basically, now we're going to start our trip from this large elliptical galaxy that we have here, and we're going to take the road down. So I don't know if you want me to stop here, or should we maybe take the first step of the compact massive galaxies?
I think you can continue a little bit more. Yeah.
Perfect.
More or less half of the talk.
Yeah, fine. Okay. So we're going to start with this. Is going to be our first stop, compact massive galaxies. They are defined by having masses larger than 10.5 solar masses, more or less, but they are smaller than 2 kiloparsecs. Actually, you can see that there's not a lot of them. And the main issue is that this criteria that we use to cut, let's say it's a little random, no? And here, this table exemplifies what I'm saying. This is from a work that summarizes the different works that have been trying to find or characterize them. And you can see that there are many mass limits, different compact criteria. So this makes that once you try to figure out how many of these galaxies we can expect in the local universe, the numbers are completely bananas. No, it goes from like basically nothing to many of them. So this is something that we, as a community, are trying to work towards, no, on how to create proper limits for these galaxies. But regardless of that, no, giving it some room for it. How can we how can we create these galaxies? Well, if you remember the cartoon that I just showed you like 2 seconds ago, what can happen, no, is that once we have this large elliptical galaxy somewhere around here, for whatever reason, it falls in a cluster, interacts with another galaxy, etc., etc. It goes to a phase of stripping that it's going to remove all these outer parts that it did, going back to square one, no, like being a red nugget. So in this case, we're going to follow a process of stripping. But also what happens is that mergers are stochastic effects. So this means that we can avoid the second phase, or well, it's expected that some of these galaxies will not undergo the second phase, and they will be left as they were in the high redshift universe. And this is what we call massive relic galaxies. So in this case, they are born here intrinsically. They don't come from a larger galaxy. What it also can happen is that we are seeing something similar to this, no, or this process of forming a massive galaxy, but later in time. That started, instead of forming early on, it started later in time. And that's what we call late bloomers. So it will also be intrinsic galaxies that they just come to be as compact and massive in here. Regardless of which is the true nature of this one, they are all important and like precious, because they are a window to these stages here at high redshift. But from the easiness, no, of being in the local universe, which means obviously less observing time, etc., etc. What are the properties in general? And I'm just going to be talking about the properties of these galaxies, but very, very generally, because I don't have time. Each one of the stops, no, would be a proper talk. So, but later on we can discuss more on it. For the compact galaxies, we see, for example, that the morphologies, sizes, and kinematics and density profiles are exactly as those as we see in the high redshift universe. And again, here you have the mass size relation that I was talking about before with a sample of compact massive galaxies. And you can see that the line that of redshift that fits them better, well, not fits, I mean, that it's underneath, is the one that corresponds to redshift 2. When we study the stellar populations to see how they are, we see that they have a range in ages from very young to very old, and also the star formations. For example, we have this typical relic galaxy that basically it's the star formation history, how much mass is accreted over time. And you can see that basically all the galaxy is created by in less than 1 giga-year. Whereas we have some other that instead have residual star formation that could either be the stripped or maybe the late bloomers. When we look at the images of these galaxies to see, you might say, well, maybe they have been no stripped. How can you know? Well, we have really deep imaging to see if there's any signs of interaction. And there are also a few works that look at the dark matter content, at the dark matter halos of these galaxies, that they are completely untouched. So all this points out that for some of these galaxies, they are like truly these relics or untouched galaxies. And also very important is that at the beginning, when all this came to be, let's say, basically there were no simulations that were trying to reproduce these galaxies. But in the recent years, because this caught the attention of many people, there's been a bunch of simulations that they have been trying to reproduce and form them as a relic galaxy, and they did very nicely. So at this stage, if we just wanted to make some crude numbers, we could say that for the compact massive galaxies, the majority of them, they have an intrinsic nature. They have been formed where they are. 40% are roughly of relics, and 45% are roughly these late bloomers. And only 15% of the galaxies that we see that they are compact correspond to galaxies that they were something larger and that has been stripped. Obviously, there's still a lot of ongoing issues in this field. And one of them is, for example, is there any environmental dependence on which type of compact massive you're going to get? And the other one is knowing how many of these galaxies are in like larger, like really large volumes. Because so far we've always been focused on smaller surveys and so on. So for example, it would be very, very interesting to know how many of these can be found in Gaia or DESI, because they are observed at the end. In order to tackle some of these questions, I'm part of this survey that it's called INSPIRE, Investigate the Stellar Populations in Relics. That basically it's a well sample of 52 compact massive galaxies at intermediate redshifts that uses ex-situ at the VLT. And this has the advantage that the ex-situ covers from the infrared to the near ultraviolet. And the near ultraviolet is a kind of unexplored regime. That it's very important because very recently there was this work from Salvador Rossinyol that showed that if instead of using the optical part of the spectra, we use the ultraviolet, we can start differentiating. For example, here you have like the contribution of very young components. They are sub-percent values, but they are there, no? So for these galaxies that for a long time we thought that they were dead and red and dead, no? They are maybe not. So obviously the question is, if we assume that relics were completely dead and red from redshift 2, but now we study them in the ultraviolet, are we gonna see also these younger components? So this is what we are doing now. So this is work in progress with Nuria Salvador-Rossignol, that we have 10 compact massive galaxies that are supposed to be relics, and we are observing them and analyzing them in this regime. On the meantime, too, what I'm testing is if we can apply the different techniques, like the full spectral fitting, no? That it's very well understood how it works in the optical, but we don't know yet if it's going to be useful for this regime. So I'm testing this too. But these things are going to be very important, not only for the upcoming multiplexing surveys like the INSPIRE that I just showed you, or WIF, for example, that I'm part of, but also because this opens the possibility of observing the stellar populations of high redshift galaxies, no? Because this part of the spectra, the ultraviolet, is shifted to what we see in the optical instruments.
Do you think we can make the stop now?
Yeah, I was going to do it here. I was going to say, so this is the next stop of the journey, so we can make it here.
Okay, thank you for this very nice introduction, and you can ask questions if you wish. And questions? Comments?
This is Paolo. Hi. Yeah, I have maybe even too many questions. I'm lost actually. So what I see, okay, you have different colors and symbol here, but suppose that I'm colorblind. I see a spread about the ellipticals, the circles. I see a spread in size for the same mass.
Yeah.
So, I mean, I know you're trying to now explain where the origin could be, but nevertheless, whether it is stripping or it's intrinsic, let's say, okay, they're all intrinsic. What is the origin of the spread? In the end, you have to get the same mass, but a very different size.
Yeah.
Why do I get an elliptical at the bottom or at the top? What is the difference, the physical reason why I end up with a different size? And before you even answer that, what is the definition of the size? Because do they have the same density profile or luminosity profile? So there is not really an issue of defining the size, or would the size depend on the profile, and therefore the mass and the size are kind of are they really correlated to each other or not?
Okay, let me see. So the issue of the size, so all this is obviously related with the physical size, that it's not even physical, no, the effective radius.
What is the definition of effective radius? Sorry, because
I've
read
like
of the
luminosity that is within half of the luminosity of
half of the luminosity.
Yeah.
But of course, it's not okay. So it's not necessarily the mass; it's the luminosity. So I guess then the star formation history may affect that relative to the mass.
Yes, exactly. So one of the reasons, so one of the things that we need to see, for example, is for these galaxies that we say that they are completely old, no, or and dead. We need to do spatially resolved studies, for example, to see if that happens at the entire galaxy, not at the very centers.
Okay.
Right. But when you move to these galaxies that they are very compact, you're basically covering already just the center, no? So even though we have done especially resolved studies of these, showing that there's basically no difference between the very internal part to the outskirts of it, but this is like really we are seeing the bulges, what it's inside of the elliptical galaxies. So we are having this remnant, either because they are naked or not, either because nothing happened and they just were left like that, or because they were back to stripped. But it's giving us the access of knowing what happened at a higher redshift.
Okay, but what creates a spread of almost an order of magnitude in size for the same mass? So, like in the region around 10 to the 10 stellar masses.
Yeah, well, this is the problem here. This is where actually one of the transitions, one of the scales happens, and that can be also an issue with, again, because putting this criteria, that you separate them at 10 to the 10, but some of these galaxies actually could be from one type or the other. So that's what lately we have been saying, that instead of following this line here, that's what it was said. If you follow it, maybe there's not that much, there's not this scatter, but just like this just goes down a larger scatter, because also here it becomes harder and harder to measure the sizes.
But let's take even two 10 to the 10. I mean, even the gray circles, they still have a scatter that is significant. I mean, imagine that's a real scatter, that's a real different sizes at the same mass.
Yeah.
At the same mass. So I'm asking physically, what do we understand why galaxies of the exact same mass can have size that is 4 times or 5 or 6 times larger than another galaxy? And is it actually does it even happen in the simulations?
Yeah.
Okay.
Yeah, no, absolutely. See, so here, let me put it because it's under this one. Yeah. So this is the one that I showed at the beginning. So for example, no, here that you would have 10, the 10 to the 10, right? So you can have a variety of sizes for different properties of these galaxies. And they are related to the different properties like the velocity dispersion or the mass to light ratios, the IMF also. But you can move through this parameter space and they all exist in it. Yeah,
although the cartoon doesn't, the cartoon doesn't have a lot of for pure ellipticals, the cartoon doesn't give a lot of scattering sizes. Right, the observations have a much larger scatter for pure ellipticals.
Yeah.
So I maybe just different merging histories or different, I don't know, different spin parameters, something. You know, I have no idea.
See, there's actually one paper that exemplifies this precisely, this scatter, and it shows, I think they separate into the 14 different types of galaxy here.
I see.
According to how much they rotate, their lambda, etc.
Okay, so elliptical maybe is too large, too broad of a definition. I see.
Yeah, okay. Actually here there's also like lenticulars are included in this. In general, yeah. Because here we're talking about like early type galaxies, so not as pure on the definition of elliptical, but so here there's elliptical and lenticulars.
Okay, thank you.
Can I ask also, Anna? You mentioned these 3 ways of getting the compactness of the massive galaxies. One of them was late bloomers.
Yeah, I made up the name.
So actually, I just didn't understand, why this late bloomer, and there was a second one, I don't remember the name. Why would it make the radius to be smaller? Yeah, the relic galaxies also. The first one, strip, is clear, but can you explain why these relic galaxies and late bloomers would be smaller?
Yeah, because basically we are at this stage, and at this stage, this galaxy that it's a red nugget, it has precisely this size and this stellar mass.
You mean in the stage of formation, basically other galaxies would accrete on a bigger halo, and somehow these ones didn't accrete? Exactly.
So relic galaxies are defined precisely as not undergoing this second phase. They only go through the dissipative. They don't have the accretion. They don't have an interaction with any other galaxy, so they don't accrete any material, and therefore they don't grow in size.
But so why they don't accrete any material? Just isolated halo? Or?
No. Actually, some of the relic galaxies that we have found and we've studied and confirmed, they are in the clusters. No.
Okay. It's in the clusters.
They're found in both places, but also in the center of the clusters. It's like contraproducing, no? But at the same time, from one side they're very massive, and they are in a region with a lot of interactions, but they avoid getting with anything else, no interacting.
But why? So what makes them different that they do not accrete other small galaxies to form this kind of more extended halo?
Just pure luck, stochasticity.
But I mean, is there a theory or something there? Because we would like to understand what makes them compact, right? So is this just
it's the other way around? Like, I think the thing is that usually you understand galaxies as this large, no, and this big, but because you are only left halfway of the path, you are left with the bulge, with a really compact and massive and dense part of the galaxy.
I see.
You are not building up the entire galaxy.
But there is no theory for why some galaxies would not develop this more extended accreted halo.
It's not theory, it's just probability.
Well,
there are some theoretical papers that that develop the numbers and everything, and more or less tells you how many would we expect in the local universe, not to go through this phase and so on. And I think it's 0.1% of the massive galaxies should not do this. But this is not 0.1%. We are well below.
But this is based on some kind of theory, the simulations, some analytic models. I don't know.
Yeah. Well, this is the two-phase formation. It's a simulation.
This is based on some simulation that basically one interprets as meaning this, but of course, for galaxy formation is not a well understood process. So then it must be some assumption, right?
Yeah.
And then how about late bloomers?
Okay, this is more of a, because one of the issues that was coming on at the beginning when there was, let me go back here in this one, no? So this is how the number density of these galaxies evolve with time. And as I said, so at high redshift, there's quite a lot of them. And then there was a decrease, and some works did find some that would follow the trend, and then some other works found like none, and then some others found like too many. No, so sorry, I just got lost on myself. Where I was going with this? The late bloomer. Sorry, yeah, sorry. So one of the claims that was there is that. It's not only that they are evolving, no, in size and through cosmic time, but also that we are starting to put, no, these new galaxies that are starting to follow that path. No, they're starting to form maybe instead of at redshift whatever 10, they're starting to form later on. So we're going to be seeing them delayed. So that's what I mean by late bloomers. No, they start all this path later in time. So by the time they start here, this is no longer the Big Bang. This is maybe redshift 3. And now they are going through this part. Maybe the physical processes, they don't need to be exactly the same, because obviously the conditions that they were very early on, they are not the same as later in the universe. But maybe no, we're seeing these galaxies that are late.
So they form later, but why would they make them have smaller radius at a fixed mass?
Because they just follow the same process as the other ones, but just later in time. And so by the time that we see them here, they really show still like these properties. So they have not finished to develop. They have not yet started, for example, their other.
It's not clear why this would make them smaller, because the accretion of a more extended halo can go at any time. So it's not clear why this would make them smaller.
Yeah, but the accretion happens on the second phase, not before.
But why would? Well, anyway, I think that's not clear that there is any theory here that really makes a solid prediction.
No,
I thought this is
like the
okay. Well, I'm going for too long, but so I don't want to.
Like the two-phase formation scenario is the theory on how you form massive galaxies, rather than hierarchical or just monolithic and
but in cold dark matter, of course, any halo will constantly accrete smaller halos at all times. This is not something that stops.
Here it's still, so the processes that happen here, I'm not saying they are not accreting. No. All this is like, these are typically wet mergers, no, this first phase. And the second phase is more dry mergers.
Sorry, the late bloomers, are they the ones for which the ages are, you had an age distribution histogram before? Would the late bloomers be the one with the younger age, or am I totally off?
Yeah, they would have recent episodes of star formation, because they started.
So is that actually the definition of late bloomer? The ones that belong
no. Late bloomers is, I mean, to be honest, I talk about them because it's 1/3 option, but.
Oh, I see.
Besides, like relic galaxies, they're very well defined, no, and how to strip galaxy too. The other one is just to exemplify that actually this type of star formation history could be either because this galaxy has been stripped, but also because if you have galaxies, this one is very extreme, it has a very old and something very young, but then I have some other galaxies that they have a more extended star formation history that it's similar of what we see in low mass elliptical galaxies, no?
Okay, so actually you don't have a definition, you don't have an empirical distinction between late bloomers and the others. It's just an assumption, an idea of what could be the origin for this.
Yeah.
Okay.
For the late bloomers, it's just like, well, and that's another option of because if I only say the other two, then people are like, oh, but they couldn't be them, you know, like galaxies forming later. Well, and it's true. So, okay. So then I put it. But the two definitions are like relic galaxy, no, or strip galaxy.
Okay, I think you can continue with your seminar.
Okay, so now we leave these compact massive galaxies and we go through the part that it's defined as compact ellipticals. Sorry for the names, I didn't make them up. I don't think they are very distinctive, but in this case, there are about 200 of these galaxies known, and they have these lower masses characterized from 10 to the 8 and 10 to the 10 solar masses. But now the sizes are smaller. The cut is around 1 kiloparsec down to 100 parsecs, more or less. So kind of this regime. Again, the limits are blurry, you know, but more or less to define them. And these galaxies, they were interesting because although they are very compact, they have these high densities that are the same values or very similar to the ones that are seen for these giant ellipticals or the compact massive galaxies. So obviously, the first time that they were found, they were said, well, then they are simply the result of stripping one of these larger galaxies, and it just leaves you with the core part of it. But the problem came because some of those started showing in isolation in the field. So obviously then they have to be formed intrinsically in here. They cannot come from something larger, because how are you going to strip something if you have, there's no other galaxy to strip or anything. In this case, for example, for the simulations, there are not as many, things are getting more complicated, but the simulation here shows you, for example, that at a given stellar mass and the size, again, you have here the extended family, and these are compacts that are observed. You can see that some of those can be obtained by stripping a larger one of these galaxies, whereas other of these galaxies can be formed in situ, as compact and with this mass. So they can exist in there. And actually, one other of these simulations, it actually shows that they can be formed in situ in this place because they can be the merging of massive star clusters, but they don't come from something larger. I guess the main difference here is always trying to see if they came from something bigger or they just were formed as we see them, regardless of their channel. When we study the stellar populations, what we see is particularly, so here again, you have the stellar mass size relation for the extended family, for compact massive galaxies, and for compact ellipticals that I'm showing here. And the color code is by age. And if, regardless of exactly what is the age they have, you can see that basically this blur of colors would be roughly equivalent to what you see here. So it's like shifted a couple of orders of magnitude here. But when you look at the metallicities that these galaxies have, they are on average always higher than the more massive ellipticals, and actually more similar to compact massive galaxies. One thing that we can get from the metallicity is that if we put the values of this metallicity with the stellar mass of the galaxy, that there are very well-known scaling relations, like the one here in this solid line shows you the mass metallicity relation for massive galaxies, whereas this one here with the dashed line is the metallicity for low mass galaxies. When you put the compact ellipticals, you can see that here the compact ellipticals of different compilations are all the circles. you can see that they are all outliers in the relation, or the majority are outlier in this relation, which would be indicative of this stripping origin. Whereas you do have some of these galaxies that do follow the scaling relations at these intermediate masses, and these galaxies would be better understood then if they form as we see them. So if we make some rough numbers of the studies that have been done so far, again, like all this is a very new field. Most of the works have been done in the recent years. Now we see a trend that is changing, because now we see that the majority of these galaxies are the result of stripping, about 25%, 85% of them, whereas we do find some, not negligible and still quite high, but only 15 of them, 15% are formed intrinsically as these, you know, like as they are in their mass, low mass, but very compact. The problems we have are actually very similar to the ones we have for the high at the high mass n, and is that we still don't know if there's an environmental dependence on where these galaxies are going to be mostly of the stripping of this origin, or whether they're going to be intrinsic ones, because it seems in general that field or isolated galaxies are of the intrinsic type, whereas those in clusters or groups are the result of stripping. But there have been found some galaxies in the other way around. So we still need to understand. But again, in order to be able to address this properly, we need better statistics, because we are just working with 200, 300 of these galaxies. So again, it's very important that we start looking for them in larger volumes and so on. And in terms of being more particular about their properties, one related of what Paolo was asking before that I said about the 2D information, we need to study them spatially resolved, because we want to see if we are recovering just the central part. If we do long slit spectroscopy, we're going to be obtaining only the information from the very center, for example. But with 2D information, we can start recovering, for example, the kinematics and the stellar populations, and see really what are the origin of these galaxies. This is all work that is in progress and should be actually published soon, because the Ferré report came back very nicely. So yeah, hopefully it's going to be out soon. So keep your eyes peeled for it. And the last stop actually now takes us to the to the less massive ones of these compact objects that are called ultra-compact dwarfs. Just by side, here you might say, oh, and for this one you have way more than for the other galaxies. It's true. So they have been detected and like classified as UCDs, but instead there are less studies about them, because this is getting fainter and fainter, so it's getting harder and harder to get good signal-to-noise data to do the stellar populations and the kinematic studies. But we follow more or less on the same dichotomy of being stripped or being intrinsic. In this case, the UCDs take the part that are 10 to the 6, 10 to the 8 solar masses, and below 100 parsecs, more or less. So very, very tiny. So almost like point-like. Some of them, particularly in this area, between 10 to the 6, 10 to the 7, they are all mixed with the parameter space that would be occupied by globular clusters. So actually, one of the possible origins that has been shown is that these galaxies, these UCDs, are the high mass n of globular clusters. Okay, whereas there are some other works and some simulations that they show you that if you follow these lines of stripping, if you strip a galaxy that is around 10 to the 10, 10 to the 9 solar masses, either dwarf or elliptical, you will make it to this type of galaxies that we see. Again, because they are very concentrated they are very concentrated, they have a high density.
Anna, you have 3 minutes more.
Vale. Okay, perfect. So I'm just going to say that in general, what we've seen so far for these galaxies, is that they are all, or the majority, stripped, whereas there are only a few that can be of this intrinsic type. And then the last part of it, it's about the supermassive black holes that they can have. And it's because when you look at the ratio between the dynamical mass and the stellar mass of these galaxies, no, with over the mass range, you can see that here, precisely between 10 to the 6 and 10 to the 9, that it's where UCDs and compact ellipticals are, there's this big spread, no, and this deviation from the 1-to-1 relation, which means that the dynamical mass is way higher than the stellar mass, which would indicate stripping, but also indicates the presence, or can indicate the presence of a supermassive black hole, a black hole. If we understand that the relation between the massive black hole and the mass, for example, no, for local galaxies follows this universal scaling relation, and we have at the high mass n the supermassive black holes. But what we can study is, okay, if they follow this relation to the low mass n and they are in there, they're going to have these intermediate black holes. But if they are outliers in this relation, then they're going to be the result, no, of something larger. For the compact massive galaxies, what we see is that once you put them in these scaling relations, they are all extreme outliers. So here, for example, these lines, they are between 3 and 5 sigma from the scaling relations. And this is only because they are left as natural outliers once they follow, no, following that cartoon of at the beginning, the supermassive black hole and the galaxy start forming, and by redshift 2 more or less, the supermassive black hole is full in place, but the galaxy still needs to grow a little bit in size because of this second phase, no? Sorry, in size, in mass for the second phase. So because in relic galaxies, we don't have this second part, they are left naturally outside. But what happens when we go to lower masses, and this is a kind of like puzzle that I've made from different works. Well, you can see that to start with, compact ellipticals, there's basically nothing yet that we know. For the UCDs, some of them, they do seem to be outliers, whereas there are a few other ones that are okay with being in these intermediate black holes. What it's clear though is that we need more detections, in particular in this part. So this is going to be just like super quick, just to say that that's what I'm doing right now. So with Mateu at the ICE, we are looking for X-ray and AGN signatures on UCDs and compact ellipticals to find out, no, how many of them do we have. For example, for the X-rays, we found about 30 of these objects have X-ray detection that we cannot rule out as being a low accreting supermassive black hole. And only 4 of them, that they are all compact ellipticals, they have an active AGN. And we are doing all this basically to see if the scaling relations with a black hole mass that they have always said, no, that they can be extrapolated to the low mass n. But recently there was a paper saying that there might be a flattening on it after at the characteristic mass scale that we were talking at the beginning. And once we add these lower and compact massive galaxies, no, it does seem that there's this flattening. It could still be due to a scatter. We do know there's a lot of scatter at the low mass n, but maybe, no. But again, this, like literally, I made this plot this week. So this is just to show a little bit on what I'm working now, trying to see if the scaling relations with a black hole would follow all the way to the low mass n. So this is just the final slide that kind of summarizes what we've been talking about, that it's this road trip where basically we do see that there's a swap in the main origin or nature of these galaxies, in the sense that for the massive ones, they are the majority intrinsic galaxies that they form as we see them, either because they are relics or because they are still forming, but they are intrinsic. They are not the result of stripping a larger galaxy. While we pass this border, kind of, things start to go the other way around. And then we have more and more galaxies that are the result of stripping, until we only have like just a few that could be accounted for forming as we see them. And the ongoing issues that you can see that they are all common in them is it has to do that we don't know yet the exact fraction of one or the other, no, of a strip versus intrinsic, and we won't be able to really account for this until we have large statistics for it. And that's it.
Thank you very much for this very beautiful talk. Questions?
Yes, Paul again. So in the upcoming survey, like the studies you're doing now, what fraction of those new ultra compact galaxies will be in clusters versus in the field?
In this one, for the X-ray, for the supermassive black holes, or
for example, but actually it's a general question. I mean,
no, the general.
In upcoming surveys, what fraction can we hope to find of this galaxy outside of clusters?
Yeah, that's actually the main issue, and one of the reasons for why we have so many numbers of the UCDs, for example, is that because they have been found in clusters, basically. So the majority of UCDs are in clusters, but not because they don't exist in the field, but because clusters is where it's easy to find them. And all the ones, for example, for WIF, where we're going to be looking them, it's in clusters. That's why I'm saying that it would be probably interesting to try to find them in Gaia or DESI, or that it's not biased on the environment.
So I understand if they're found outside of cluster, then stripping it would be hard to understand.
Yeah.
But if they are in cluster, is stripping well understood? Either because I wonder, I mean, if even simulation can model this accurately, because you have to model the individual stars inside the galaxy to model to simulate the stripping correctly. It must be computationally a difficult problem, right? Or is stripping actually at least at a theoretical level understood that is no problem to understand these galaxies due to stripping if they are inside clusters?
Yeah, no. Actually, for the UCDs, so historically, let's say it was the other way around. Like UCDs were the first ones to be found, and then compact ellipticals, and then the compact massive galaxies. So at the beginning, those were the ones that people were trying to understand. And in that case, the stripping scenario was very easy to use, and both from the theoretical and from the observational part. So again, studying the stellar populations and the kinematics of them, they are compatible with the properties that we see in the centers of these larger galaxies. So no, stripping is very easy actually for these ones.
But I didn't mean observationally. I mean
no. Also simulations. See, the only problem is that for these ones, there are less simulations that because this is very specific, right? So, for example, there's only these three kind of simulations that reproduce this. These are theoretical tracks.
Oh, from stripping, from simulation
from stripping.
Stripping.
Sorry, yeah, these are theoretical tracks. This is not
Okay.
observational or invented.
Okay.
Yeah.
We are a little bit off the time, but if people want to remain for discussions, they can remain. We officially finish the talk right now. Okay. We thank you, Anna, again. We cannot clap here, but okay, thank you very much to all for participating.
Thank you. I'm gonna stop sharing.
Anna, I have a question, a stupid question.
No,
can you hear me?
Why stupid? No.
Do people understand why all the galaxies seem to have a black hole in the middle, in the center?
No, actually, I mean, we say that, but it's not completely sure because we are not able to measure them all. And what happens as you go to lower masses is that actually some of the galaxies have been found that they might not even have a black hole at all.
But it's not ruled out that so far there is no galaxy that it was proven that there is no black hole in the center.
As far as I know, no.
And could there be a reason that the galaxies cannot form if there is no supermassive black hole?
Yeah, so actually I had, but I don't think it's in this talk. I do have some simulations that show the relation on how can you build a supermassive black hole in these compact galaxies or the other way around. and I mean, the relation with the galaxy is very tight all the time. So honestly, I would expect them to be everywhere. And that's why we are extrapolating all this to the low mass n, where we don't know what's happening, because clearly I showed you there are like 5 UCDs that have been, you know, measured. So we are extrapolating this, assuming that they will all, they all should show the supermassive black hole, because they come from stripping a larger galaxy that should have a supermassive black hole. But if they come from a dwarf galaxy, for example, that it's not that clear that they have supermassive black holes. So yeah, it's very theoretical yet. I mean, observationally, it's very hard to find and to measure, and yeah, you can only get indicators for it, like the difference in the mass ratios and stuff like that.
I see. Thank you.
That is Paolo again. I'm still puzzled by the stripping thing. I struggle to get the whole picture in my mind. If I mean, there must be a large number of ultra compact in clusters. Maybe even the majority of galaxies are ultra compact.
Not the majority, but there's a lot of them.
So I mean, if
in cluster there might be, you know, say hundreds.
If they're reduced in mass so much by stripping.
99% stripping, kind of.
No, I mean, a lot of the mass is reduced. Then there should be more stars in the clusters floating between galaxies than inside galaxies. I mean, is that really observed that there are so many stars outside of galaxies in clusters?
I don't know.
I mean, the evolution in the simulation, you reduce the mass by a factor of 10. So 90% of the gas that was of the stars that were in the galaxy are now outside of the galaxy. And this happens to maybe half of the galaxies in the clusters.
Or it has been accreted, no? And now it's the envelope of one of the other galaxies. They can be just transferred, no? It doesn't need to be.
Yeah, I don't know, maybe.
Usually they are, so the thing is, like, some of these galaxies, and that's why we know that stripping works too, is because we see them in the moment of being stripped, no? So you can clearly see the interaction, and we've been studying how they interact and so on. So all these stars that you are disrupting from this UCD are gonna end up being the buildup of this larger other galaxy. It doesn't need to go back to the interstellar medium, no?
So you start with like a mass distribution of elliptical in a cluster, and then the smaller ones are the one that get stripped preferentially, something like that.
I think, Paolo, that's okay, what Anna is saying, because it's, you know, even though there are some compact galaxies that may be losing a lot of their mass by stripping, it's not all the galaxies, first of all, right? And then actually, I think when you look at a cluster, you normally have this central galaxy. They're called sometimes CD galaxies in the center, that they have these outer halos, which are very highly extended, right? They have power laws that are, you know, flatter than r⁻⁻3. So when you try to integrate the total stellar mass, you never see the place where it starts converging. So it goes into basically this intracluster light. And I think intracluster light can easily be 25–30% of all the stars in a cluster. So it's, I think it's not a problem, probably.
Okay, so there is strong evidence of those stars floating around. It's not.
Yeah, intracluster light. Yeah,
okay.
It's hard to detect, but I think it is there.
Okay.
Yeah. But usually I get the other way around. What people don't believe in theory, you know, or they think it's harder to understand is the relics, not the stripping. The stripping, they assume it's like a given. Okay, so guess we can leave it here.
Looks like there are no more questions. So thank you, Anna, again.
A pleasure.
Thank you very much. Bye.
Thank you, and see you soon.
Thank you.
Bye.